Good afternoon, everyone. Welcome back, and thank you for joining us. I'm Steve,
And I'm Scott.
and together we are Backyard Musings, the Science and Technology channel.
Yeah, and we're finishing up the day talking about space and specifically black holes. And these things fascinate me. Um, and this story is right up there. So, very cool.
The size of a black hole formed by the merger of two orbiting black holes can be predicted using simple thermodynamics. Of course, simple thermodynamics. Two, two black holes locked in orbit do not remain apart forever. As they spiral closer, they eventually collide in an extraordinarily energetic event that warps the surrounding universe and sends gravitational waves across billions of light years. These waves, which are ripples in the fabric of space-time continuum, can be measured by highly sensitive instruments on Earth. Their signals allow physicists to estimate the properties of the larger black hole left behind after the collision known as the remnant. Would you like to know more?
So, is this like one big black hole taking over a little black hole?
Yeah, yeah,
Just
yeah.
kind of what a bully, huh? Kind of a bully. Yeah. All right, making those predictions accurately usually requires supercomputers to solve the difficult equations Einstein developed for general relativity. Physicists led by Penn State now have shown that a much simpler thermodynamic principle may closely predict the remnant size while also revealing more about the physics hidden within those equations.
Yeah, there are physics hidden in the equations, believe me.
Yeah.
Those
Yeah.
equations are next level.
When we get off the air, I'll explain all that to you, Steve, if it's over your head. So,
Oh, please explain it now, Scott.
no, I don't want to embarrass you. I'll wait.
Okay. The research was published in Physical Review Letters on July 7th, 2026, where it was selected as an editor's suggestion. Quote, the final black hole after merger is ringing like a struck bell, and it radiates away more gravitational waves until it settles into a calm, stable state described by just two numbers. Wow, two numbers. Its final mass and spin, said Monica Rincon Ramirez, a postdoctoral scholar in physics in the Penn State Eberly College of Science, and the first author of the paper. Continuing her quote, the question we asked is, can we predict what the final state looks like using arguments from thermodynamics?
Okay.
Valid question.
What's that?
Valid question.
Valid question, right? And this what I'm about to read may give some answers to that for us simpler folks. Thermodynamics describes how energy, heat, and entropy determine the large-scale behavior of systems made from many interacting particles. Its principles apply to everything from gases inside engines and the atmosphere to the physical changes involved in cooking. There you have it. Simple terms.
General relativity approaches nature differently. It describes gravity as the curvature of space-time and is essential for explaining astronomical phenomena such as black holes. These objects were once thought to lie outside thermodynamics until Stephen Hawking demonstrated that black holes could radiate energy.
The researchers considered what remains after gravitational waves carry energy and angular momentum away from a merging pair. Angular momentum measures the rotational motion of the system.
Their calculations. What?
I couldn't have said it better.
This is exactly what you're about to explain.
Yeah.
Their calculations suggest that the resulting black hole settles into the state with the greatest possible entropy once those losses are included, a strange phenomenon. Entropy describes how many possible arrangements a system can have and reflects the tendency of physical systems to move toward more probable, less ordered states.
Quote, entropy is essentially a measure of disorder, or more precisely, of how many ways something can be arranged. That's according to Vashek Prasad, a postdoctoral researcher in astronomy and astrophysics at at Penn State and an author of the paper. Going on with a quote, a messy room has a high entropy. There are countless ways things can be strewn about. A perfectly tidy room has a low entropy. There are only a few arrangements that count as tidy. Okay. Nature tends to drift toward high entropy states simply because there are more of them. Our results suggest that black hole mergers do something similar. Okay.
I don't know. That's too simplistic. Nature tends to drift toward high entropy states simply because there are more of them. I don't know. There's got to be some calculations in there.
Sure.
I don't know. The researchers call their proposal the maximum entropy conjecture for black hole mergers. The idea closely resembles how ordinary thermodynamics predicts the final condition of familiar physical systems. Quote, when two hot gases are brought into contact, one does not need to track every microscopic interaction of the molecules in the gases to determine the final state of a combined gas, said Eugenio Bianchi, professor of physics at Penn State and author of the paper. Maximizing entropy while accounting for other physical laws predicts the outcome.
The new conjecture proposes that the same broad rule could determine what remains after two black holes combine. To test it, the researchers followed how the mass and angular momentum of two merging black holes corresponded to a sequence of possible rotating remnants. They then identified where entropy reached its highest value and compared that point with a remnant independently predicted by numerical relativity simulations. Of course.
After two black holes merge, the resulting object appears to lose nearly all information about the collision that created it. What remains can be described almost entirely through two properties, its mass and spin.
Quote, this work explores a surprisingly possibility at the intersection of gravity, black hole physics, and thermodynamics that goes way beyond the established laws of black hole mechanics and thermodynamics and raises a potentially transformative question. Could entropy maximization be a fundamental organizing principle governing black hole interactions more generally?
Inquiring minds want to know, right?
Sure. Yeah.
Way over my head.
Yeah. Wait. This is
what I can get from this is don't get caught in the gravity of a black hole.
Yeah, or don't be anywhere around two black holes if one of them is about ready to swallow the other one up. So, because if you're in that one black hole that's going to get swallowed up, you'll probably never get out.
Never.
Right?
Never.
Yeah. So, anyway. Okay.
All right, folks. Thanks for joining us.
Take care, everyone. We'll see you on the next one.